In the previous section, I talked about how carbon-14 was an unstable isotope, and cobalt-60 was also an unstable isotope, and if you waited around long enough, those isotopes underwent beta decay. Well, uranium-238 is also unstable. Uranium-238 is an isotope of uranium. If you wait around long enough, it also undergoes decay, but it decays differently than carbon-14 and cobalt-60. So this is uranium-238. It's a very heavy type of atom, and again, what I want you to do is watch for the fancy animation right around the part that I'm circling. So we have an unstable isotope of uranium-238. If you wait around long enough, what will happen is a different type of decay. What happens with uranium-238 is the atom will essentially spit out 2 protons and 2 neutrons. So let me just back up. Here are 2 protons, here are 2 neutrons. If you wait around long enough, they get fired out of the center of the atom, out of the nucleus of the atom. And if you remember, or you can look this up in your periodic table, 2 protons and 2 neutrons have a mass of 4 daltons, and the element that has 2 protons is helium. So basically, what you can think of uranium-238's decay as is you can think of it as firing out the nucleus of a helium atom. It fires out 2 protons, and helium has 2 protons, and it fires out 2 neutrons as well. So the total mass of everything that gets fired out is 4 atomic mass units, or 4 daltons. So to emphasize again, if you wait around long enough, uranium-238, that isotope, will fire off a helium nucleus, and the uranium-238 itself will decay into something else. This type of decay was the type of decay that was found first. And because of that, it's called alpha decay. And so alpha decay is when you have an unstable isotope that fires off 2 protons and 2 neutrons, which is usually written as helium nucleus. It's called a helium nucleus instead of a helium atom because the thing that got fired off, the 2 protons and 2 neutrons, does not contain any electrons. So it's just the inside part of a helium atom, which is called the helium nucleus. So again, the question is, what does the uranium-238 turn into? What is this question mark over here? And we can figure this out by basically looking at the decay reaction and trying to balance it. Again, the weight of everything on the left has to equal the weight of everything on the right side of the arrow. Well, the isotope of uranium that we had a weight or a mass of 238 daltons. So everything on the right has to have a total mass of 238 daltons. The helium, we already said, had a mass of 4 daltons. So whatever this question mark is, it has to have a mass of 234 daltons, because 234 plus 4 will equal 238. So we now know what the mass of this question mark is. It has a mass of 234. The other thing that we need to know, or the other thing that we need to balance, is the number of positive charges. Uranium has an atomic number of 92. What that means is it has 92 protons, or 92 positive charges. The helium has 2 positive charges because it has 2 protons. So the question mark has to have 90 protons. It has to have 90 positive charges, because 90 positive charges plus 2 additional positive charges from the helium will equal the total number of positive charges that the uranium had at the beginning. So now we know that this question mark, whatever it is, has to have a mass of 234, and it has to have an atomic number of 90. And then if you look up in the periodic table what element has an atomic number of 90, you'll see that it's thorium. So this is basically how you figure out what the missing element is, or it's how you figure out what the unstable isotope turns into. If you wait around long enough, uranium-238 will spit out a helium nucleus, and the uranium-238 itself will turn into thorium-234. And this type of decay, when you fire off a helium nucleus and turn into something else, is called alpha decay. On this slide, we're going to do another example of alpha decay. So this is similar to the beta decay exercises that we did in the previous section. I'm going to show you a decay reaction, and I'm going to show you a question mark, and you try to figure out the question mark. You can pause at any point and try to figure this out on your own. But here we have an isotope of polonium. This is the symbol for polonium, PO. This isotope is polonium-208. And what I am saying to you by drawing this reaction is that polonium-208 undergoes alpha decay, and the polonium-208 turns into something else, which I'm representing by a question mark. The question is, what does it turn into? So the way to deal with this, again, it's like balancing an equation. The weights of everything on the left side of the arrow have to equal the weights of everything on the right side of the arrow. So the polonium has a mass of 208. The helium nucleus, which is sometimes called an alpha particle because it's usually part of an alpha decay reaction. So if someone ever says an alpha particle, what they're really talking about is this helium nucleus here that has a mass of 4. So we start with a mass of 208. Everything on the right side has to have a mass of a total mass of 208. So the helium has a mass of 4. The question mark has to have a mass of 204 because 204 plus 4 is equal to 208. Then you're going to need the periodic table. You look up polonium and you say, well, how many positive charges or how many protons does polonium have? Oh, polonium has 84 protons. So 84 positive charges on the left side of the arrow. There have to be a total of 84 positive charges on the right side of the arrow. 2 of those positive charges are already accounted for by the helium nucleus. What that means is the question mark has to have a total of 82 positive charges or 82 protons. So whatever this question mark is, it has an atomic number of 82. You look it up in the periodic table, and the question mark turns out to be lead, which has a weird symbol. The symbol is Pb. So polonium-208 will undergo alpha decay, and it will turn into lead-204. And just to show that in a slightly simplified form, polonium-208 undergoes alpha decay, it spits out a helium nucleus, and it turns into lead-204. So that's just a different example of alpha decay. And the other thing to point out about alpha decay is that in alpha decay, whatever isotope and element you start out with, if it undergoes alpha decay, it will turn into an isotope of an element that is 2 to the left on the periodic table. The reason that it will always be 2 to the left is because whatever isotope you start with will lose 2 protons because it will spit out a helium nucleus. So it'll lose 2 protons. And so whatever it turns into will have 2 fewer protons. So you go from polonium and you step 2 to the left on the periodic table. This is in contrast to beta decay, where you gain a proton. So with beta decay, you go up 1 on the periodic table. With alpha decay, you go 2 steps down on the periodic table, or 2 steps to the left.